Hello, welcome to a video where we look at methodology 10.1 and solving 2 by 2 first order linear homogeneous systems of ordinary differential equations with constant coefficients. And the example we look at here is y1 prime equals 2y1 plus 4y2 for the first equation, and y2 prime equals 4y1 plus 2y2 for the second equation. And we have initial conditions. Y1 at 0 is 5, and Y2 at 0 is -1. We'll start off with step 1, writing the system in the matrix form. And you can see the constant coefficients will make up that matrix, and then we'll shift y and y prime to vectors. So we'll do a little vector arrow there. So 2, 4, 4, 2. And that matrix is A. All right, then we will take that matrix A and we'll subtract lambda times the identity matrix. So A is 2, 4, 2. And the identity matrix is just ones in the diagonal and zeros in the off diagonal. And when we multiply that by lambda, which is a scalar, it just gives you lambdas in the diagonal. And then 0 times lambda is 0, 1 times lambda is lambda. And then when we subtract, we just subtract component-wise. So we'll only subtract the lambdas in the diagonal. All right, now we're going to try to find the eigenvalues of A by finding the determinant of this matrix, A minus lambda I, and setting it equal to 0 and solving for lambda. So lambda is the eigenvalue. All right, so for the determinant, we multiply the diagonal components. So we get 2 minus lambda times 2 minus lambda. And then we subtract the product of the off diagonals, which is 4 times 4. And then the determinant is set equal to 0. So this will give you a quadratic equation. And if we expand this out, we get 4 minus 2 lambda is 2 lambda plus lambda squared minus 16. And then cleaning stuff up, lambda squared minus 4 lambda minus 12. All right, so if you're lucky, you can factor this and get 2 real values, or 1 repeated real value. But if you can't, then you'd use the quadratic formula, and you may end up with some complex values. So there's 3 cases, depending on the nature of the solution set here. And we'll just do the distinct real values in this example. And then the handout covers the repeated root in example 2, and then the complex roots in example 3. So this one just factors. And then setting each factor equal to 0, you get lambda 1, our first eigenvalue is 6, and lambda 2, our second eigenvalue is -2. So each eigenvalue has a corresponding eigenvector, and really it's like a whole line or direction of vectors. And so we'll figure out that direction, and then we'll pick a specific vector in that line for convenience. And we got to do this one at a time. So we'll start with lambda 1 being 6, and then find the eigenvector x1 that goes with it. Get a little more room here. All right, so starting with lambda 1 equals 6, you can see our formula. We do a minus lambda 1I times x1 equals 0. So subtracting that specific eigenvalue, we're still subtracting it just in the diagonal components. So we put a minus 6 there, and then a minus 6 here. So that's the matrix A minus lambda 1I. And then x1, we're going to use x1 and x2 for the components of the vector x1. I know that's not very good notation, but they're just temporary. We're just using them in this one step, and then we'll discard them and reuse them in the next step. And then that 0 is the 0 vector. So since people coming into this class may not have linear algebra background, we actually go back to the expanded equation form here, rather than solve this with linear algebra techniques. So we'll just turn this into a regular system. So again, multiply the first row by that vector, or take the dot product of the first row and that vector, and you get negative 4 times x1 plus 4 times x2 equals 0. And then the second row of the matrix dotted with the vector 4x1 minus 4x2 equals 0. So there's the system. Now, either equation should give you the same result. If we take the first equation, we get negative 4x1 equals negative 4x2, and that tells me that x1 equals x2. If I take the second equation, I get 4x1 equals 4x2, and that dividing by 4, negative 4, you get the same thing. So the vector x, the eigenvector x1, sorry, all we have to do is pick so that x1 and x2 are equal. So any vector where those are equal, which is sort of like a vector, or the line where it's the slope of 1, or a 45-degree angle. Now you don't want to pick 0, 0, because the 0 vector is a trivial eigenvector for any system that's homogeneous with the eigenvalue of 0. So we want non-zero. And so we'll be boring and just pick 1, 1, but you could pick anything you want as long as these have the same components, right? These are all eigenvectors. The easiest one to pick is the vector 1, 1. All right, so we found the eigenvector x1 that goes with lambda 1. And now we'll repeat the process with the other eigenvalue. Our other eigenvalue, lambda 2, was equal to negative 2. So when we go to set up this matrix, we're subtracting negative 2 from the diagonals. And so we're going to use x1 and x2 as the components of the vector x2. Feel free to use better notation. But again, once we found this, we won't even need x1, x2. We're just going to be using that, right? All right, so this is actually 2 plus 2, and so we'll get 4, 4, 4, 4. So 4 4s in our matrix. And then multiplying that out, and get 4x1 plus 4x2 equals 0 for both equations. So here it becomes even more obvious that we can pick either equation we want to get this eigenvector relationship, because they are the same. So let's say 4x1 equals negative 4x2, and then dividing by 4 get x1 equals negative x2. So the eigenvector x2, it can be any vector where the components are opposites. So I'm going to pick a vector that has first component 1 and second component -1. Though here, val1 is just as easy to work with and just as many negatives, right? So really, it's kind of just personal preference as to which of those you used. And again, you could use, um, 5/3 and -5/3, right? So that would also be fine. But I think I'll use the first one, 1, -1. All right, so we've got eigenvectors and eigenvalues. What does this have to do with the solution? We're actually ready to jump to the general solution. So the general solution is C1 times the vector x1 e to the lambda 1t plus C2 vector x2 e to the lambda 2t. So we will, state this, which again, it's a vector with y1 and y2 as the components. That's our solution. And then for x1, right, we had 1, 1. And then lambda 1 was 6. And then for vector x2, we're doing 1, -1. And then it was lambda 2 was -2. So that's the general solution. And I mean, you could write it as a system. All right, you just use the vector components to kind of identify the two equations. So if you don't have initial conditions for your initial value problem, then that's your general solution and you're done. If you have initial conditions, you can find a specific solution. We were given initial conditions at the very beginning. We were told that y1 of 0 equals 5 and y2 of 0 equals -1. And you could also think of that as the vector y at 0 is the vector 5, -1. So all we do is replace t with 0, right? This is t equals 0. And then replace y1 and y2 with 5 and -1. All right, so for y1, we got 5 equals c1. And then these exponentials, they're all e to the 0, which is 1. And so they all just disappear, right? E to the 0, e to the 0. And then the second equation, we get c1 minus c2. So we get a little system here to solve and find c1 and c2. It's set for doing kind of an addition method, where c2 minus c2 is 0. And so we can get c1 equals 2. And then c1 plus c2 is 5. So c2 is 3. All right, so let's write out our specific solution. C1 is 2. So you can put the 2 in there, in the vector, or you can leave it outside. And then for the 3, yeah, let's put that one in there too. It seems like it's just a little neater to do that. So I replace C1 and C2 with 2 and 3, and now have my specific solution for the initial value problem. All right, so how do we validate this? You can validate the initial conditions by replacing t with 0 and making sure you get 5, -1. But to check this with the differential equation, you need to find y1 prime and y2 prime, and you need to compare that with the right side of the differential equation. So, I mean, let's just rewrite the original system. So at the very beginning, we were told that this is the system. So if I find y1 and y2 prime, then I can also set up the linear combinations of y1 and y2 on the right sides, and I can just make sure those match up. So let's do y1 is 2e6t plus 3e -2t. So y1 prime is 12e6t minus 6e -2t. All right, and so then for the right side, it's 2y1 plus 4y2. So y2 is 2e to the 6t minus 3e to the -2t. So we do 2 times y1 plus 4 times y2. And distributing, and then combining like terms, the e to the 6t is 12 e to the 6t, and then the e to the -2t is 6 minus 12 is -6. And then you're looking for agreement between those two expressions, which are the left and right sides of the differential equation. And they match, which means that checks off. Right. Let's do the other one. So derivative of y2 is 12e to the 6t plus 6e to the -2t. And then the right side, we got 4 times y1 plus 2 times y2. Again, distributing, and then combining like terms, 8 and 4 is 12, and then 12 minus 6 is 6. So get the end of the surface here. And those match up as well, so we have validated the solution with the differential equation. And that concludes the example 1. Now, when you go to example 2, you're going to get the second case in step 3 where the solutions to the quadratic are a single value. Lambda1 and lambda2 are both 1. So you can still go through step 4 the same way using that value of 1. But when you get to step 5, you'll need to set up a slightly different formula. And so we'll use a minus lambda 1i times u equals x. And then finding the vector u, you can set up a second second eigenvector. So when you look at the general solution, the first term is the same, using lambda1 to go with the vector x1. But for the second part, we have this vector u times e to the lambda 1t, and then our vector x2 e to the lambda 2t, which is lambda 2 is lambda 1, so I guess that should be changed. Yeah, that should say lambda 1 there. Sorry. I mean, really, it could just say lambda because we're just using lambda. We could drop the subscripts. All right, so that's the repeated root case. And then in example 3, you're going to get complex eigenvalues where the real part is alpha and the imaginary part is beta. So you can follow along with the directions, but if you get stuck with that one, go ahead and check out the Trench textbook, chapter 10. And these 3 cases are covered in the sections 10.4 is the instructor model, 10.5 is the fill in the blanks, and then 10.6 is the your turn. And what I did was I just picked this example 10.6.1. So this is the complete worked solution, and you can kind of follow along with that to make sense of how to deal with those complex eigenvalues. All right, well, that should do it for our final methodology. Thank you so much, and hopefully you enjoyed the course.